welcome to the 11.1 notes. I'm going to let you read through the description or introduction of chapter 11 on your own. It explains where calculus came from and why it's important. And we are going to focus on jumping right into 11.1, tangents. So a couple of the vocabulary words that we already talked about a little bit in class. Rate of change. And rate of change, remember, is looking at the slope of a line between 2 points. So on any function, we can pick 2 points, find the slope between those 2 points, and that would give us the average rate of change, okay? For linear functions, it's called a slope. For nonlinear functions, it is not a slope because nonlinear functions don't have slope, okay? One of the things that we can find the average rate of change for is a velocity vector. So the example that we're going to focus on for this section, we're going to look at average velocity so that we can kind of visualize, because velocity is really just the vector for speed, so the direction and magnitude for speed. So we have an average velocity, and that is our average rate of change. And the new thing that we're going to look at in this section is the instantaneous velocity. So remember, when we were talking about this in class, we talked about how average velocity or average rate of change is between 2 points. So we have some time and some distance. Instantaneous velocity is the speed or the rate of change at just 1 point. And so we haven't really seen that before because we would have to divide by 0. We would be looking at instant, so the time would be 0. And we can't divide by 0. And so the way that we look at this is by looking at the average velocity, which was through 2 points, as the secant line. So we looked at a parabola. We can pick 2 points. The line that goes between those 2 points is a secant line, or the instantaneous, which is just 1 point. And we discovered that the line that goes through that just one point is called the tangent. Okay, so we have a tangent and a secant. So let's look at an example. In our first example, we're just going to look for the average velocity. Okay, well, velocity is speed. Speed is miles per hour. Miles per hour is distance over time. And we're talking about the change in distance. How far have I gone? So we can use delta to represent that it's a change in distance divided by a change in time. So in example 1, we're looking for the change in distance divided by the change in time. An automobile travels 120 miles, that's our distance, 120 miles, in 2 hours and 30 minutes. So that's our time, 2 hours and 30 minutes. Well, if I'm going to be dividing this, I want my answer in miles per hours. So we want to divide by just hours. So let's convert that denominator. 120 miles per 2.5 hours. So then we have 120 divided by 2.5. 120 divided by 2.5 miles per hour. And 120 divided by 2.5, I'll check it on my calculator. 120 divided by 2.5 is 48 miles per hour. Is an average velocity. So that doesn't mean I'm traveling 48 miles per hour the entire time. I'm not traveling 48 miles per hour for the entire 2 hours and 30 minutes. However, if I take all of my speeds throughout the entire trip, it averages out to 48 miles per hour. Okay, so that doesn't mean we're traveling the same speed the entire trip. If we wanted to find the speed at just one instance of time, because it's an instant of time, there's no change in time, right? So for example, if I wanted to find out how fast I was going at 1 hour into the trip, there's no change in time. And so our change in time, our denominator would be 0, but we can't divide by 0. And so we have a new method of trying to solve that using limits. So if we look at the next page, kind of re-summarizes that to find the instantaneous velocity, we would have to divide by 0, but we can't divide by 0, so we need to use the limit. And the limit that we're going to use is the limit of what would make the denominator 0. Okay, so let's recall limits. The limit as x approaches 5 of f of x. So again, I'm just going to use a parabola as an example, but it could be any function. Okay, and if we choose to look at when x is 5, we have a point on our graph. But the limit is not interested in that point. The limit is what's happening around that point. So what happens as x approaches 5? And what happens as x approaches 5 from either direction? And as x approaches 5 in either direction, our f of x value is getting closer and closer to whatever value the y value at that point is. So if our graph is continuous, then our values will be approaching the value on our graph. If the value is not discontinuous, if the graph, so if there was an asymptote or something, then that's not necessarily the case. So we cannot assume that the limit as x approaches 5 of f of x is equal to f of 5. We cannot assume that. If it's continuous, that will be the case. But if it's discontinuous, that will not be the case. So let's look at an example where we can kind of look at these limits. We're going to start in example 2 with just kind of taking it step by step. We'll start by looking at a ball that's rolling down a ramp so that its distance, s, from the top of the ramp after t seconds is exactly t squared feet. Okay, so what does this look like? If I have a ball rolling down a ramp, at the top of the ramp at 0 seconds, the ball is 0 feet away from the top of the ramp. After 1 second, the ball is 1 foot away. After 2 seconds, the ball is 4 feet away. After 3 seconds, the ball is 9 feet away. So what we have is a parabola, well, half of a parabola, right? So what is the distance the ball has traveled after t seconds? Well, that was actually given to us directly from the problem. After t seconds, the ball is s feet. It has traveled s feet. Okay. What is the average velocity of the ball over the first 2 seconds? So we're looking from t equals 0 to t equals 2. Well, how far has the ball traveled, right? Velocity is distance over time. So how far has the ball traveled? Well, the distance we said was s, and s equals t squared. So we have well, over the first 2 seconds, right? So we have the second minus the first. So t2 squared minus t1 squared. Let's call this t1 and t2. The distance. So at time 2, we're at 4 feet. At time 0, we're at 0 feet. So we have 4 minus 0 as our distance. And then we have our change in time. Well, time, the difference between 2 and 0, so we have t2 minus t1, which is 2 minus 0. So we have 4 over 2. We have 2. Distance is feet per second. Right, so we're substituting in. In order to find the change in distance, we subtract the 2 distances. Well, distance is our y values, and time is our x values. So the difference in distances in 2 seconds, we went from a distance of 4 and a distance of 0. So the difference, the distance between them, is 4. Time went from 0 seconds to 2 seconds. So to find the difference in time, we do 2 minus 0, which is 2. Simplifying that, we have our average velocity over the first 2 seconds is 2 feet per second. So then we want to find, okay, that's our average velocity. What is the instantaneous velocity of the ball at 2 seconds? Okay, so now we're looking at just t equals 2. Okay, well, at t equals 2, my change in time would be 0. So if I try to do this using the average velocity, change in distance over change in time, well, at 2 seconds, there has been no change in distance, and there has been no change in time because I'm only looking at one instance of time. And this is undefined. Okay, so what we need is we need to use limits. At t equals 2, we want the limit as t approaches 2. We're approaching 2 because we're interested in what is the slope of the tangent line when the time is 2. So we're looking at what happens as our time approaches 2 of our change in distance. Okay, so our distance, we start at some point on this function, right? And that point is getting closer and closer to a time of 2. So this point here, we can say has coordinates t, comma, s, which is t squared. Okay, this is the time, this is the distance. So to find the difference between these, my point is getting closer and closer to 2. We start with our distance of t squared minus where we want to end up is our distance of 4 divided by. And now we're looking at the change in time. Well, at time t, and we're getting to time 2. So t minus 2. So now we have the limit as t approaches 2 of t squared minus 4 is factorable. We can factor it t minus 2 times t plus 2 divided by t minus 2. We can simplify this rational expression. And so we get the limit as t approaches 2 of t plus 2. Well, as t approaches 2, the value of t is changing, right? That was why we chose this point that can move. And so what would happen if t is 1? Then we get 1 plus 2 is 3. What if t is 1.5? Then 1.5 plus 2 is 3.5. What if t is 1.75? 1.75 plus 2 is 3.75. So these values are all getting closer and closer and closer to, these are approaching 4. We can also see that if we substitute the t value here, we get a value. And because this is continuous, we know that that value will be the value of our limit. So we have 2 plus 2 equals 4. Now this is a rate of change, right? This is a velocity. So 4 feet per second. Okay, so again, if we look at the diagram, I have the graph drawn here as well. Okay, we're looking at time 2, what is our instantaneous rate of change? And in order to find the instantaneous rate of change, we're taking a point and we're taking points closer and closer and closer and closer to 2 so that we can find out what is the slope between those points. So every time we pick a point, we're looking at the slope of the line between those points until we get to a slope that only touches the graph in one place. And the slope of this line right here has a slope of 4. Okay, so we can use this in order to find the instantaneous velocity, but notice this is also the same process that we would use to find the slope of this tangent line. So if we're looking at example 3, we want to use the limits. We want to use the limits, as we were just discussing, in order to find the slope of the tangent line. Slope of the tangent line, same as instantaneous velocity. Okay, so if I want to find the slope of the tangent line at 2, 4, 2, 4, that's what we just did in our previous example. We need to find the limit as t approaches 2 of the distance between this point and any arbitrary point on this graph, t squared. So we start with the change in y values, the distance, t squared minus, this point here is 2, 4, minus 4, divided by change in x's, the difference in time, t minus 2, equals, as we just saw before, limit as t approaches 2, t minus 2, t plus 2, t minus 2, equals 4. Okay, but what if we had a different point? So let's see what happens if we have another point, this point 1, 1. Well, we're going to follow exactly the same process. So we want the limit as t approaches not 2 now, but 1 of difference in x, or difference in y's, t squared minus 1, divided by difference in x's, t minus 1, equals the limit as t approaches 1, factor this, t plus 1, t minus 1, divided by t minus 1, equals the limit as t approaches 1 of t plus 1. Well, just like before, if we substitute in values of t that get closer and closer to 1, what we find is that since this is continuous, we would get 1 plus 1, which is 2. Now, we're not looking for velocities here, so it's not feet per second, right? We're looking for just the slope. Slope is a number, a scalar, so the answer is just 4 and 2. Let's take a look at the next page. So starting at the top of the next page, we have another new name for this same concept, okay? So the instantaneous rate of change, which we said is also the slope of the tangent line, is also called a derivative. And this is the word that you'll hear most often in calculus, derivative, okay? So since velocity is only one application of calculating this rate of change, we can now apply this for instantaneous other measurements, okay? So instantaneous acceleration, for example, okay? So we have these formulas. For any function, y equals f of x, the average rate of change, remember this is the one that's related to the secant line, that goes through 2 points, of y with respect to x on any interval ab can be calculated this way. The difference in our y values divided by the difference in our x values. Remember, it's a slope of a secant line, so it's the same formula that we use for slope, okay? The derivative, or the instantaneous rate of change, or the slope of the tangent line, can be calculated as the limit as x approaches a of f of x minus f of a divided by x minus a. Notice there's no b here because we only have one value, x is a, right? Here we had 2 values, we had a and b. So a and b are in our formula. Here we have only a, and so our second value comes from some unknown point x. Okay, now, because we want this denominator to equal 0, the other way of looking at this is we call the denominator h. So if we let our denominator be h, we're looking for when h is 0. And then if we substitute that, since x minus a equals h, then x equals h plus a, or a plus h. And so we have another formula to find the same value, the derivative, okay? And we said that this is the slope of the tangent line. So that's why we still have y's over x, y values over x values. Okay, so let's try applying this derivative, okay? So we said instantaneous rate of change is the same as a slope of tangent, which is the same as derivative. Derivative we can denote, if you look back at our definition, with a little apostrophe. F prime of A. Okay, if we generalize this to variables, we can also say that f prime of x for any value of x, right? If I don't know which point I'm approaching, I want to just find it for any point. F prime of x can also be written dy dx. And this means the derivative with respect to x. Okay, it's clearer to see the slope here, the relationship of y over x, but all of these represent the same thing. This one is generalized to be for any value. These have values usually given to you. So let's look at example 4. So for example 4, let's go ahead and use our second formula here. So f prime of 4 equals the limit as h approaches 0, f of a plus h minus f of a divided by h. And then we need to substitute. So f of a plus h, I'm substituting a plus h in for x. 2 times the quantity of a plus h squared minus 3 minus f of a, so in parentheses 2a squared minus 3 all over h. And I forgot to write my limit as h approaches 0. Should be in there. Equals the limit as h approaches 0 of 2 times a plus h squared, so that's a squared plus 2ah. Let me actually write this on the next line. Equals the limit as h approaches 0 of 2 times a squared plus 2ah plus h squared minus 3 minus 2a squared plus 3 all over h. Distributing the 2, we get 2, the limit as h approaches 0 of 2a squared plus 4ah plus 2h squared minus 3 plus 3 goes away, 2a squared all over h, 2a squared goes away. So we get the limit as h approaches 0 of 2h squared plus 4ah over h. I can reduce by h. So we get the limit as h approaches 0 of 2h plus 4a. Well, a is 4. So this is h is 0 and a is 4. 2 times 0 plus 4 times 4 equals 16. Okay, you can substitute a in at the beginning. Substitute with the 4. That's fine. You'll get exactly the same answer. Okay, and you can use the other formula as well. You should get exactly the same answer. Your steps will look very different though. And lastly, let's look at example 5. In example 5, we're doing the same thing, finding the derivative, but this time we're not given a value. So we want to find f prime of x. Again, I'm going to use the second formula. That's the most popular formula to use for derivatives. So it's a good one to see used more often. The limit as h approaches 0 of f of a plus h minus f of a divided by h. Now our a value is x, so I'll substitute x in here. So f of a plus h, the limit as h approaches 0 of f of x plus h minus f of x divided by h gives us the limit as h approaches 0 of this whole thing squared. So x plus h squared minus x squared divided by h. Simplifying now, x plus h squared is x squared plus 2xh plus h squared minus x squared over h. Simplify, simplify. So the limit as h approaches 0, dividing by h of 2x plus h. 2x plus h is continuous, and so we get 2x plus 0, h is 0, gives us just 2x. So notice we can take the derivative of a function, but our solution then will be a function. I didn't have a value substituted in for a, so my output is not a value. So if I found f prime of 7, the answer should be 14. Because now I have a function that gives me the derivative no matter what value I put in for x. Let's try another one. We have dy dx for y equals 1 over x. Same exact thing, right? dy dx just means f prime of x. So dy dx is f prime of x, which is the limit as h approaches 0. I'm going to skip right to where we substituted x in. F of x plus h minus f of x divided by h. And now we substitute these into our function. So the limit as h approaches 0 of 1 over x plus h minus 1 over x divided by h. We need a common denominator here. So we get the limit as x approaches h of x minus the quantity of x plus h divided by x times x plus h all over h. That was by finding the least common denominator here. So then we have the limit as h approaches 0 of x minus x is 0, so we get just negative h divided by x times x plus h. Dividing by h is the same as times 1 over h. Simplify that. Negative 1 over x squared plus hx. Limit as h approaches 0. So finally we can substitute in. So we get the limit as h approaches 0 is negative 1 divided by x squared plus 0 times x, which is negative 1 over x squared. Okay, so we could do that with any function. This is kind of an example of a couple of different functions that we can do. And this process that we're doing where we're simplifying and taking the limit is called finding the derivative. Go ahead and write your summary reflection and put your answer to the question in Edpuzzle.